In the previous episode, we discussed space. Concepts like space and matter are, of course, much more profound than we might imagine. So, aside from these, what are some other basic concepts that seem plain but hold deeper mysteries? Finally, we come to this question: what is time? Imagine, for a moment, that you are an alien visiting Earth. You often wander around coffee shops and grocery stores, trying to learn how humans talk by eavesdropping on their conversations. You'd notice something strange. People often talk about time, but they almost never discuss what the true nature of time is. We check the time every day and talk about bad days, good days, days far in the past, or crazy days. We save time, stick to time, set aside time to do things, and also often waste and kill time. We notice when time is up, when time has passed, when time ends, or when time runs out. Time waits for no one. Sometimes, time flies, sometimes, it passes quietly without us noticing, and sometimes, it feels like time drags on forever. We often feel like there's not enough time, but what exactly is time? Is it something as real as matter and space, or is it an abstract concept that transcends our experience? If you expect today's physicists to provide a clear answer to the profound mystery of time, it might still be too early. The true nature of time remains one of the biggest mysteries in physics. But there's still much we can discuss about it. Let's first talk about how time is defined. Among all the questions related to the universe, the most interesting ones are often the seemingly simple ones. However, this is a question that is extremely difficult to answer. When you scratch your head and still can't think of an answer, you realize that we actually don't understand the basic things we think we know so well. These fundamental questions might awaken us to the fact that our understanding of them has been fundamentally wrong all along. Once we obtain clear and precise answers, our perspective on the universe and our place within it will be dramatically transformed. The first step is to define what time is. Ultimately, this is the approach physics takes to solving complex problems. When describing a physical problem, we must start with a clear definition, then use mathematical descriptions, logical reasoning, and experiments to verify it. So, how should we define time? If you were to randomly interview people on the street and ask them for their definition of time, you might hear answers like these. Isn't time simply the difference between the past and the present? Time seems to be what tells you when something happens. Isn't time just what the clock shows? Of course, these definitions all make sense, but they also have many issues. For example, the first response suggests that time is the difference between the past and the present, but how do we define the past and the present? The second response says time tells you when something happens, but how should we define when? The third response equates time to what the clock shows, but isn't the clock itself bound by time? It seems that our exploration of time has hit a bit of a roadblock. Even the first step of defining it proves incredibly challenging. However, we don't need to feel too anxious. This is the nature of tackling a familiar yet fundamental concept. When it comes to defining time, humans often have an intuitive sense of it but struggle to articulate an accurate description. This phenomenon is not unique to time. Similar questions exist in other disciplines. For example, what is life? A topic biologists have debated for decades. One reason time is so difficult to define lies in our rigid impressions of it from daily life. Time connects the now of the past with the now of the present, what we call the present moment. However, the present moment is fleeting and elusive. You can savor the memory of eating chocolate cake, but you cannot pause or even grasp the present moment itself. Every instant transitions from a vivid experience to a memory of the past. Time also involves the future. The ability to predict the future based on past experiences is crucial for survival. Whether it's a prehistoric human preparing for a harsh winter or a modern individual looking for a phone charger, planning for the future is essential. Without a sense of time, survival would be nearly impossible. In physics, the concept of time is equally indispensable. The very definition of physics includes time. For example, Wikipedia describes physics as the study of matter and its motion through space-time. Motion itself depends on time. A core task of physics is predicting future events based on past occurrences, making any discussion of physics meaningless without time. However, any definition of time is inevitably influenced by daily experience. Even the act of contemplating time requires time itself. To illustrate this, imagine a mischievous friend planning to throw a water balloon at you. Now picture 6 snapshots. 1. You leisurely walk home, unaware of the prank. 2. Your friend holds a water balloon, ready to strike. 3. You insert your key into the door lock. 4. Your friend launches the water balloon. 5. You get drenched. 6. Your friend laughs uncontrollably. Each snapshot represents a moment, showing the positions and actions of you and your friend, static frames like panels in a comic strip. Without the concept of time, the universe would appear as a series of unchanging images. Fortunately, the universe is not static. The concept of time connects these still images in 2 ways. 1. Time arranges the images in a sequence, giving them order. Scrambling the order, for instance, showing you soaked first and then unlocking the door, would feel nonsensical. And 2. Time also connects these 6 images through causality, meaning what happens at one moment determines what happens next. This is the principle of cause and effect. For example, if your friend hadn't thrown the water balloon, you wouldn't have ended up drenched. Physicists work to uncover these causal relationships, which help us understand what changes are possible or impossible in the universe. With these established laws, we can predict potential outcomes based on one static snapshot while ruling out others. It is because of time that we grasp the patterns of change and motion. Without it, we could only imagine a static universe devoid of transformation. How can we connect these abstract concepts of time with our everyday experiences? We can visualize the 6 static snapshots being strung together at very short time intervals to create a seamless movie. The shorter the intervals, the smoother the sequence. The mathematical method frequently used in physics, calculus was developed for precisely this purpose. It combines many infinitesimally small quantities into a continuous variable. Similarly, while watching a film, the high frame rate prevents us from perceiving individual frames, creating the illusion of smooth motion. In the same way, the operation and evolution of the universe can be seen as a series of static frames governed by physical laws. Time dictates their sequence and rhythm. If you still find this definition of time unclear or unsatisfactory, you might have to wait longer. Physicists, philosophers, and even your friends have debated this topic for centuries. Even today, there's no universally accepted definition of time. Even physics textbooks rarely tackle this question directly. One of time's mysteries is its resistance to precise definition. It's deeply intertwined with how we perceive and understand the world. At best, we can discuss it abstractly, but pulling it apart to examine its essence remains challenging. All tools we use to determine our place in the universe implicitly assume that time flows forward continuously, a premise that is mostly accurate. Since time's definition remains unclear, we can ask more questions. Why does time exist? Why does time seem to flow only forward? Is forward the only direction time can flow? If time is part of space-time, why is it so different from space? Amid these questions, one stands out: is time the 4th dimension? If you think of time as a continuous track along which events unfold, you might naturally recall a similar fundamental concept: space. Just as an event can be divided into static frames over time, a motion can be broken down spatially. This similarity invites us to consider a close connection between space and time. In fact, modern physics suggests that space and time are remarkably alike. In many cases, time can be thought of as a navigable dimension. Before diving deeper, let's simplify this idea using a model of the universe. We are familiar with three-dimensional space, but let's simplify it to one dimension. In this space, you can only move along one direction. Now, imagine how you and your prank-loving friend would live in this altered dimension. In the morning, your friend wakes up and begins their busy day. Before you return home, they make several trips to the water balloon store, obviously for their mischief. Now picture a diagram with 2 points. The top point represents the water balloon store, and the bottom point represents your house. A straight line connects these 2 points. Your friend moves back and forth along this line. This movement in one-dimensional space can also be represented on a two-dimensional space-time graph. Let's visualize how this graph might look. Previously, we described a one-dimensional diagram with 2 points connected by a vertical line, showing your friend's motion between these points. Now, let's treat this vertical line as the y-axis, representing space. Perpendicular to it, we add an x-axis, representing time. Over time, your friend moves consistently to the right. In this coordinate system, where the x-axis is time and the y-axis is space, your friend's movement forms a sine wave. However, don't celebrate too soon for grasping this analogy. Comparing time to space doesn't mean time has all the attributes of spatial dimensions. Time fundamentally differs from space, and these differences arise from time's unique properties. By examining these distinctions, we hope to better understand the broader concept of space-time. Keep that graph in your mind as we continue. So, what sets time apart from space? Comparing the two highlights their similarities, but, more importantly, emphasizes their differences. Your relationship with time is distinct from your relationship with space. First, you can move freely within space. You can walk in circles, turn back to where you started, or change your speed, moving faster, slower, or stopping entirely. But on the timeline, your freedom is much more constrained. Your movement along time is uniform. 1 second always equals 1 second, precisely. You cannot go backward in time or take a detour. You can't whimsically return to a previous moment and appear in a different place. While you can visit the same place at different times, you cannot exist in different locations at the same time. Returning to our space-time graph, let's clarify this. On the graph, the x-axis represents time, and the y-axis represents space. Recall the sine wave shape. You can revisit the same spatial point at different points on the x-axis, different times. In everyday terms, you can go home today and return tomorrow. But the reverse isn't possible. You can't revisit the same time at different spatial locations. Reflect on that sine wave again to better understand this concept. You cannot find the same x-coordinate value at different y-coordinate values. In simpler terms, you cannot appear in two different places at the same time. Looking at this coordinate system, things seem a bit strange. When we draw a sine curve on this coordinate system, fixing the y-axis, space coordinate, allows multiple possible x-coordinates, time values. For example, when y equals 1, x can be 0, 0.5, 1, 2, and so on. However, the reverse is not true. When the x-axis, time, is fixed, the y-axis, space, must be precisely and uniquely defined. This means we cannot draw any arbitrary figure in this coordinate system, as the x-axis and y-axis have some fundamental differences we don't yet fully understand. If this sounds confusing, just draw this coordinate system on paper. Let the horizontal axis represent time, x-axis, and the vertical axis represent space, y-axis. Following the idea that you can visit the same place at different times but not be in different places at the same time, you'll see the logic. This strangeness lies in the nature of things. It feels normal for something to have a fixed location, but not for it to have a fixed time. This is because time flows forward like a wave, and past moments never return. In contrast, your position in space is much more flexible. Some places you may never visit in your life, while others you frequent often. From birth to death, time flows in a single direction. Movement along the timeline is fundamentally different from movement in spatial dimensions. Even though our theories conveniently treat time as another dimension for mathematical purposes, we must always remember that time and spatial dimensions are fundamentally different. This distinction arises because space is composed of interrelated locations, while time is not. Time connects the freeze-frame snapshots of the universe in a way that creates causality, which dictates how we can use time. For instance, a common question is, can we travel back in time? Listeners of previous episodes might feel that nothing is impossible in this universe. Things that seemed unattainable in the past have now become part of everyday life. However, when it comes to time travel, modern physicists are confident that it's impossible. Any theory involving time travel conflicts with the fundamental rules of the universe's operation. In some science fiction stories, aliens or advanced humans can move back and forth along the timeline as easily as we walk through a corridor. While entertaining, such stories have significant flaws from a physics perspective. For example, traveling back in time disrupts causality, which is critical for a coherent universe. Without causality, events would become absurdly bizarre. Let's pause here and reflect. Why time seems to only move forward, why we can't reverse entropy, and how this could be connected to the fate of the universe itself. As we unravel these cosmic questions, we'll venture into uncharted territory where the future may not be as fixed as we think. Stay tuned for part 2, where we challenge our very understanding of time, space, and the universe's ultimate fate.